So now that we've discussed in my AP Statistics class some of the really big overarching themes for the year, including the central limit theorem and that crazy idea that even if the underlying distribution you're trying to measure, like the CEOs that we ran into earlier in the year, even if that is skewed, the sampling distribution, as long as you take a large enough sample, will not be skewed. It'll be normal-ish, approximately normal. So we've talked about those variety of big ideas, and now we're going to get into doing some examples where we solve problems using these sampling distributions. If we can do that, next semester basically we just have to put everything together. That's all we'll have left. So let's see. So can you guys help me? I forget, what is the first example about for sampling distributions that you have in front of you? Example number one. M&M's, groovy ones. So these are like weird, crazy, hippie color ones. And I might need some calculator assistance because I don't have mine ready to go. So be ready if you don't mind. So the groovy M&Ms. It says groovy M&Ms are supposed to make up, supposedly, they make up 30% of the candies sold. In a large bag of them, 250, that's a pretty big bag, what is the probability that we get at least 25% groovy M&Ms? So, what did I have there for the first thing I wanted you to do? Think. So, what are we supposed to be doing here? What question are we trying to answer? We want a probability, right? Which probability? Of what being more than 25%? You've got to be real careful about this. What size bags were we interested in? What size samples were we interested in? 250. That's the size of samples we're interested in. Could we be interested in another size, like smaller bags with 50 M&Ms? Sure. But this question said, in the jumbo size, what's the probability of getting a bag in that size that has at least 25% groovy, whatever that means, tie-dye color or whatever. You know what I'm saying?
Glittery.
That's the idea. So then I said we need to check some conditions, because before we apply these big grandiose ideas like the central limit theorem that have all this advanced math that have proved them to be true, we have to make sure that we fit. You guys remember yesterday when we were looking at the Reese's Pieces, and at the very end I said, well, it might not work, it might not be normal-ish, and Katie ran into this, and I saw a couple other people were running into this too. They put the overlaid normal model on it, and it didn't quite fit well enough. One of the situations that doesn't work quite well enough is like if the p was like 0.01, something like that. So we've got to make sure our situation is okay to model with the normal model. So what assumptions are we going to have to address? And these assumptions are big time. What assumptions do we need to address? The 10% condition. That's one of them. If we're doing proportions, we have certain assumptions. If we're doing means, we have other assumptions. Make sure you're clear on what assumptions need to be addressed where. Okay? So the first one, if you're doing a proportion problem, which I think we're doing a proportion problem because I see a proportion here. This is a percentage or a proportion, right? If that's true, I need to make sure I fit the 10% condition. This is just one of the conditions to make sure I can do my z-scores. So I can use a normal model. So what is the 10% condition? I think we talked about it the other day. Lana, you want to tell me?
The sampling size should be no more than 10% of the population.
So we don't want to take too big of a sample, right? So how do we check that? We want to say something like, how big is our sample size? 250. So I'm going to say I'm going to like ask a rhetorical question. Is our sample size, which is equal to 250, so n is 250, is that less than, you can say this all kinds of different ways, less than 10% of the entire population of these kinds of M&Ms. I'm really bad at drawing the and the other way, so sorry. So, question, right? What do you guys think? Are we safe to assume that or not?
Yes.
Why?
There's probably more than 20,000 M&Ms.
What is 10%? Like, if 250 is multiplied by 10, that's 2,500 M&Ms. Are there more than 2,500 M&Ms out there?
Yes.
Even if they're like a fancy special release of M&Ms? I think so. Okay, so I'm going to answer. Yes. We can assume there are way more than this many M&Ms, no matter what kind of M&Ms there are. Nice exclamation point. I think we're extra safe. We've definitely met that assumption. So far we're good to use the normal model. What other assumption do we need if we're working with proportions in order to use the normal model? This is a totally new one, but you're going to see it all the time from now on. The success-failure condition. So I'm just going to write that as success-failure. So a success-failure condition is that you've got to have at least 10 successes and at least 10 failures. There's good reasons for that. We'll probably run into them a little bit later. Right now, let's just check it. So we've got to make sure we have enough successes. That's going to tell you how many successes you have. And really it's n. Yeah. So, how many is that going to be for this situation? I think I left something out. I mean, I have it on your paper, but I don't have it on mine. What's the other important number here that we have left out? There's an important number, isn't it 30%? What was 30%? Is it P or P hat? It's supposedly the godly thing, right? So let's just remind ourselves of that. It's on yours, but that's P. Make sure you label things correctly. P versus P hat, totally different stuff. Okay. So we've got N, we've got P, right? 250 times P. What is that? Can you guys help me? 75? Is 75 greater than 10? Yes. So that tells me I have 10 successes. Way more than 10. I'm good to go. I've also got to check that I have 10 failures. So I'm going to do NQ. Is that greater than 10? I'm going to say 250 times Q is 70% then. Is that greater than 10? Well, duh, but let's just write it out. The AP exam loves to see these exact numbers. So it is 70%. Really, it's going to be whatever's left out of 75. So it's going to be, is it 175?
Yes.
And if you need to round on these, that's fine. It's not a big deal. But is that more than 10? Well, yeah, I'm clearly good to go. So I've satisfied both of my assumptions. Now, the book talked about another one, and it kind of like wishy-washied it, because we need to be more specific in the future. And what was the third assumption besides these two? It was something about randomization, right? So what do you guys think? When we buy a bag of M&Ms from the grocery store, is it basically a random sample out of the population of all M&Ms or not? Is there anything that would suggest like that bags were not independent or something? I think it's a fairly representative, it might not be completely random, but it is fairly representative of everything. So we'll talk about that more another day. I want to focus on these two new assumptions today. So now, yes, we can use our normal model. Let's do it. Let's answer our question. So I'm going to erase my assumptions. And actually, let's do the calculation. So, the calculation. Our normal model is going to have what parameters? And then we'll draw on it what we need. I'll put this over here, I should say. What is the mean of our normal model going to be? 0.3? Oh yeah, because it just stacks up around P. What is the standard deviation of our normal model going to be? Square root of P, Q over N. That's going to be how much spread situation has for this distribution of samples, of bags, of groovy M&Ms of size 250. It's a mouthful, isn't it? You don't have to always say that mouthful for yourself, but that's what this is. Okay, so what does that come out to? I don't know, 0.0 something, guessing. What do you got my number here? 0.029. 0.029? You guys want to confirm what Connor had? Is that 0.029? Now remember, this is the standard deviation of a sampling distribution. So let's try to name it, at least in these first couple examples, with correct symbolism. It's a standard deviation. Don't I use the Greek letter sigma for standard deviation? But it's not a parameter. It's the standard deviation of a distribution of p hat samples. So it's the standard deviation of the p hat distribution. That's its real correct name. You guys might be like, well, why am I making such a big deal about this? Because it's these subtle ideas that really affect how well you understand this stuff. So you can do a lot of them without understanding it totally, but it just depends. Depends what level of Plato's forms you want to be on. Okay, so let's do the calculation. Where should I be drawing on here? Well, I should say the middle was, of course, 0.3. And what were we interested in?
It's greater than 0.25.
Yeah, greater than.
We want the probability of getting a bag at least 25%. I think I may have left out a. No. It's 25% more or less. It's 30%. Something like this, right? I don't know exactly where it's at. Should I be shading above or below for this one? Above. So this number is going to be more than 50%, right? So let's calculate it with z-scores. So this number is exactly the same as we've done it for many, many times now. So z equals what? The x, which is like this. It's really not the x. Really, in this case, it's like the p hat, kind of, right? Minus the middle, or the mean of the sampling distribution. It's kind of weird here because it's the mean of a sampling distribution. It's not like the mean of means. It's a mean of this distribution of p hat samples. It's kind of crazy. And then what's the standard deviation of this distribution? We figured it out. 0.029. So we just need to stick that in our calculator, figure it out. So you're going to have like negative 0.05.
I got 1.72.
Oh wait, oops, I forgot the negative.
Isn't it negative?
Yeah, negative.
Negative 1.72, so I'll trust him on the math there. That looks about right to me. Yep. And then we just go to our table of z values. So when we go to our table of z values, we can figure out the probability that something is beneath that, because remember, the z table is always going to provide us the number underneath. It's always below. So I'm going to go to my z table. Just give me a moment. So on the back of my book, I found negative 1.72 gives me about 0.0427. That makes sense for this area right here. So I'm just going to put it on the curve right there, since I know that's what it might represent, 0.0427. That's this little shaded area right here, which of course is not what I was asked to find. Remember, what we were asked to find was the area above. So of course you always want to draw that picture so you save yourself in case you answer the wrong question. So the probability that z is more than negative 1.72 is the area we're interested in. So that's going to be 100% minus 0.0427, which is going to be like 0.9573, something like that. So about 95%. It's going to be the answer. So we want to make sure we put our answers in context and use the language appropriately, because that's one of the most important things in Chapter 18 and introducing sampling distributions. So what were we asked on this one? Let's have a look. I'm just going to go back since I lost track and had to start this video over. So it said, this is the groovy M&Ms problem. So it said, what's the probability that we get at least 25% groovy candies? And remember, we're working with bags of size 250. So there is a 95.73% chance of getting at least 25%, there's the visual for that, groovy M&Ms, whether these be tie-dye or whatever color that means, in a bag, well, I'm going to say not in a bag, in bags of 250 like these. Remember, you always want to stick that like these or something like it in your response because you don't want to apply this beyond the population that it represents. This sample has to apply only to the population we've sampled from. So if we perchance only sampled from, like this is not a very good example, but if we only sampled from a certain store or something, we could only apply it to that store. Or if perhaps maybe M&Ms are being produced by Mexico, Canada, and China, and we sampled from the Mexico batch of M&Ms, we wouldn't want to apply that to the Canadian or the Chinese M&Ms. So in this case, that's not really an issue because why would Canada, Mexico, and another country make different batches of M&Ms? But in a lot of cases, that is true. For example, let's look at the second example with highway speeds. So, if you look at your handout, we're going to do one more proportional sampling distribution example now. So this one says, of all cars on the interstate, 80% exceed the speed limit. What proportion of speeders might we see among the next 50 cars? So, first thing to do is to think about the problem. What are we given and what are we asked for? So, what we were given, that 80% number, it says suppose 80% of cars exceed the speed limit. You want to ask yourself, is that a standard deviation? Is that a mean? Is that a proportion? What is it? I think in this case it comes down to the 80% being the parameter proportion or the statistic proportion p hat. And since they said that's what it's supposed to be, that's supposedly godly knowledge. So that's a parameter. So in this case we're going to say that p is 80%. A lot of people speed, so I can believe it. So they say, if that's true, what proportion of speeders might we see if we choose a sample of 50 cars? So you can see that I inserted some context there. So I'm saying my sample size is 50 cars at a time. It's like you go out on the highway and you look at the 50 cars and you pick that in your sample. 1 second. And I'm back. So what else? They said what was the exact question that they wanted to know. This is also part of the thinking process. What proportion of speeders, and I want to insert the word, might we expect to see? So to me that says like we need to find the average that we'd see and then go 2 or 3 standard deviations each way. In the guide you can see I already put a normal distribution on there with the empirical rule, 68, 95, 99.7. So I think we should be going 2 or 3 standard deviations, and that's going to capture all of basically what we might see, what we expect to see. Okay, so before we use the normal model, of course, we need to make sure that it's appropriate to use that model on this sampling distribution to begin with. So we need to check a couple assumptions. So the first one is randomization. So for randomization, just ask yourself, it doesn't have to be random, but is my sample of 50 cars at least representative? As long as you don't choose something like the middle of a funeral procession, I think just picking a typical spot in the day, you're going to be okay. So you'd want to write that in a sentence maybe, but there you go. I'm going to be quick and brief today. The second thing you want to check is the 10% condition. Again, I'm going to speak this more than write it down because of time constraints and I've got to leave. So the 10% condition is we want to make sure that there are more than 500 cars on the road. So you want to ask yourself, does our sample, or excuse me, I shouldn't say does our sample, is the population of cars on, and we're examining a particular interstate, one highway, so I'm going to say this interstate, this highway, greater than 10 times n, which in this case is 10 times 50, or 500. You might not want to write that down, but that's the question you should be asking yourself in your head. So I think the answer is, well, of course, pretty much any interstate, even during just one day, you're going to see that many cars. So this is what you should write when checking the condition. I am sure we will have more than 500 cars on any such interstate. Sounds very reasonable to me. So there's a good way to check that. The other thing we need to do to ensure that we can use the normal model is, of course, check the success or failure condition. We need to see 10 successes, and then we also need to see at least 10 failures. So write those numbers out. So n was, we were looking at 50 cars at a time. The proportion of cars that sped was 80%. So is that greater than 10? You know what, I'm not sure, so I'm not going to write it like that. I'm going to say, what is 50 times 0.8? I'll use my calculator if I have to, but this time it's easy. That's just 40. 40 is greater than 10. Check. Same thing over here. 50, the success of percent of failure, or Q, is 20%. So what is 50 times 20%? I think that's exactly 10. So in this case, we made it just carefully enough. In your assignment or in the future, if this had turned out to be like 7 or 3, go ahead and carry out the rest of the computations and use the normal model. But then at the end, in your conclusion, you want to say something like, even though this is the percentage or this is the answer that I got, I need to be cautious because my normal model probably didn't fit the situation, so it's probably off. And hopefully later in the class we'll learn a little bit about how much it's off, and if you violate an assumption like that, how bad is the violation. But right now, keep doing the computation anyway. So in this case, we just barely snuck by there. We're good to go there. We're definitely good to go here. And our randomization is not random but representative. So we should be plenty fine to apply the normal model to this sampling distribution situation. So let's go ahead and do that. So when we apply the normal model, here's what we'll have. The middle of the normal model is, of course, going to be P. That's where we learned that the samples stack up at, is at the true proportion. So that should be that. So I'll say the normal model's parameters are 0.8. And then here we've got to put the square root of PQ over N. So that's going to be about, don't know, I'm going to look at it up. I think I got 0.057. Okay, so there we go. I also want to give this a really specific name because names are going to matter a whole bunch moving forwards. This is a standard deviation, of course, so I'm going to use the Greek letter sigma, and it's the standard deviation of what? Well, remember, what we're using here, the normal model, is the normal. We're using the normal model for a sampling distribution, and in fact, the sampling distribution of proportions. So I'm going to say this is the standard deviation of the p hat sampling distribution. You might think I'm being overkill here with the technicality and the symbolism, but it really matters that you're thinking about this correctly, that you're using the normal model, and specifically you're using this normal model to approximate the sampling distribution and make a decision. So the decision we were asked, if you remember, I'm sorry it's not on the board, was what proportion of cars might we expect to see in this situation. So I think we basically just want to go a couple standard deviations in each direction. So let's just go 3, that way we're pretty sure, in fact we're 99.7% sure. Well, it's not exactly how it works, but that's kind of the way we're going towards next semester. So let's go 3 standard deviations each way. So I'm going to write that the way that we just learned, 3 of these standard deviations each way. So we'll go +3 there, -3 there. +3 or -3 from what? Well, from 0.8. And you get my idea. So what is this one? This one's going to be 0.8 minus 3, and our standard deviation was 0.057. And this one is going to be, just equal sign to be consistent in my notation, 0.8 plus 3 of our standard deviations. So what do we get for those two numbers? Looks like we get about 0.971. and 0.629, something like that. So let's write out our conclusion. Our conclusion is we can expect to observe between 62.9% and 97.1% of cars on highways, or I should say interstates, but to be speeding. So I'd like you to think about what these two words that we'd like to put in here to make this extra statistically relevant and valid. What are those two blanks? The best way to say this is on highways like these. That way we're not extending to highways that are very different kinds. And I think this is probably true for most highways, but I don't think that we can assume this godly parameter of 80% speeders applies to all different kinds of highways. Highways that run through major cities are going to be different than interstate highways that run in mainly rural areas. So we definitely need this like these on this problem, and most other situations like it. I'll see you next time.